There's a very nice problem in your textbook that I want to draw your attention to. Problem number 3 on page 241. You have a monopoly, the single seller of a good, and the monopoly demand function is this. Okay. That's the demand function, or demand curve, you could call it. This demand function shows you how much the monopolist can sell at different prices. It's a simple linear demand curve with a downward slope. The monopolist has a cost function given by this equation. It's a cubic cost function. 1/3 Q cubed minus 7Q squared plus 111Q plus 50. Okay. Now, your goal is to find the price and output that maximizes the monopolist's profit. Okay. This monopolist could charge any price he or she likes, so long as it's on that demand curve. What price should the monopolist set? Or alternatively, how much output should the monopolist produce? Okay. How do you go about doing this problem, Matthew? It's been a long time since I called on you, Matthew. In fact, it may be the first time. So. Okay. Well, there are alternative ways of doing it. Now, since this is the first time I called on you, that wasn't the way I was planning on doing it, but let's do it that way. Okay. Let's take the first derivative of the cost function. If we do that, we get C prime of Q, which is marginal cost, is equal to what, Matthew? Oh. All right. We're using the power function rule to differentiate this term right here. Yeah. You bring the 3 down, you multiply it times the 1/3. But then the power on this, 3 times 1/3 is 1. Then the power on this is 2 rather than 3. So Q squared minus 14Q plus 111. Okay. So we have marginal cost, Matthew. What do we do next? Marginal revenue, okay. You have this demand curve. How are we going to get marginal revenue?
Find the inverse demand.
Okay, good, very good. Let's actually find the inverse demand. And what will the inverse demand be?
100 minus E equals 100 minus E.
Right, okay, this will be our inverse demand. Very good, Matthew. Why is it we want the inverse demand rather than the demand?
We want it as a function of Q.
Okay. All right. So what is our goal? We got this inverse demand. What's the next step?
We're going to multiply it times Q.
Yeah, okay. Because if we multiply P times Q, that gives us revenue. Okay. So P times Q then is what?
100Q minus E.
Yeah, just substitute in for P. And the reason we're doing that is because we wanted to get revenue as a function of Q alone. Notice that cost is already expressed in terms of Q. Now, we've got revenue expressed in terms of Q as well. What do we do next, Matthew?
Take the first derivative of the
Yes.
second function.
Yeah. Get this first derivative of the revenue function, R prime of Q, which is this marginal revenue. And R prime of Q is 100 minus 2Q. Okay, good. We got marginal revenue, we got marginal costs. Now what do we do? Yes, we're solving for the profit maximizing output by equating marginal revenue to marginal cost. Okay. So let's do that. Here's our marginal cost equation. Let's set this equal to marginal revenue, which is 100 minus 2Q. And then let's see what we get. Let's bring everything over to the left-hand side. Then this will become 11 over here when we subtract 100. Bring the 2Q, add 2Q to both sides, and this will be minus 12Q, won't it? So we have Q squared minus 12Q plus 11 equals 0. Okay, well, what next? Okay. Chang is kind to you. This factors. And I tell you what, if I give you a problem like this on the exam, I'll be kind to you too, and I'll make sure that you could factor it. Otherwise, you would have to do what? You'd have to use the quadratic formula to get the solution. But Chang is kind to you. And what is this factor to, Matthew? I think it factors. Yeah. What does it factor to? Can you see? Right. We could just rewrite this as Q minus 1, I'll put that one first, times Q minus 11. Notice when we multiply this, here we get our Q squared. And when we multiply this Q times the minus 11, we get a minus 11Q. And then when we multiply minus 1 times Q, we get another. So that's minus 12, which matches. And then minus 1 times minus 11 gives us a plus 11. So it factors nicely. So in this case, what are the critical values of Q? Yes, they're true critical values of Q that satisfy this first order conditions. Let's call one of them just Q sub 0. Q sub 0 equals 1. Notice if that were 1, this would be a 0. So obviously the equation would be satisfied. But there's another critical value, 11. If Q were 11, then this term would be 0. Okay. So those are the two critical values. So which of these gives us a maximum? Do either of them give us a maximum? Or do both of them give us a maximum? Matthew, actually, I'm glad you suggested doing it this way first, because this kind of points out one of the limitations of setting marginal revenue equal to marginal cost. In this case, there are two critical values. And which of these give us a maximum? Okay, one way we could approach this, do this problem, is take a graphical approach. Okay. Let's graph. Is that what your suggestion been? Graphing marginal revenue, marginal cost?
I was going to suggest that you initially do revenue function minus cost.
Oh, okay. That would be a different approach. Right. We could do that too. Okay. But we'll do the graphs later. We'll follow what you suggested. Let's take a different approach. And your approach is to start off, Ben, by doing what?
Writing profit is equal to
Yeah.
minus cost.
Yeah. Yeah. Formally, that is the way you should do these optimization problems if you can. First, find out what your objective function is. That's step one. Find out what the thing it is you're trying to maximize. So let's take that approach. But what we have here is good too. We'll come back to this. So Ben, how would we find our profit function? Okay, but actually, yeah. Okay, so we've done that, haven't we? As part of finding marginal revenue. Matthew's already found that. So we have our revenue function. So what's our profit function then? Yeah. Profit, by definition, is revenue minus cost. So we can express profit as a function of output. Is simply R of Q minus C of Q. And R of Q we have right here. So let's just substitute in for that. 100Q minus Q squared. Minus cost, and I'm going to put brackets. The cost function was given to you already as a function of Q. And recall that our cost function is this. So there's our profit function. Actually, we can simplify this a little bit, can't we? Let's simplify this a little bit by combining terms. Let's see. I'm going to start with the highest powered term first. We have a minus 1/3 Q cubed. I'm going to put that first. Now, let me see. If we look at the Q squared terms, we've got a minus Q squared. Notice we have a minus sign out here, so this will be a plus 7. Plus 7 minus 1 will be a 6, won't it? Okay, watch me to make sure I don't make a mistake here. Is that right? We got a plus 7, and we got a minus 1. Yeah, that looks like a plus 6, doesn't it? Then notice we have 100Q here. Then we have a minus 111Q, so that'll be a minus 11Q. Okay. Right? Minus 111 plus 100, yeah, that looks like a minus 11. Then we have a minus 50. Okay. So that's our objective function. That's the thing we're trying to maximize. Once you have the objective function, what's the next step? Yeah, take the first derivative. Who said that? Oh, it's Ben. I didn't see. Okay. First derivative. So pi prime of Q is what? What is pi prime of Q going to be? Okay, did you say minus Q squared? Okay, because there is this minus sign here, so the 3 times the 1/3, so it would be minus Q squared plus 12Q minus 11 equals 0. I don't like the minus Q squared, so I'm just going to multiply both sides of this equation by a minus 1. I can certainly do that. That will maintain the equality. If I multiply both sides by minus 1, I get this. Q squared minus 12Q plus 11 equals 0. And again, we can do what with this? It looks familiar, doesn't it? It should actually look familiar because setting marginal revenue equal to marginal cost is what we did before. That's equivalent to the first order condition. So, again, let's factor this. q minus 1 times q minus 11 equals 0. This gives us our two roots that we saw before. q1 equals 1. q2 equals 11. Okay? And this is just the same solution we got by setting marginal revenue equal to marginal cost. However, we now know how to proceed next, don't we? What do we do next? Yeah, we look at the second derivative. Now, be careful. This is the first derivative right here. This is the first derivative right here. This is minus 1 times the first derivative. So don't go back to this. Go back to your first derivative, which is this, which has the minus sign in front of it. And that gives us a second derivative of what, Ben? What's our second derivative? Minus 2q plus 12. Okay. Now, how does this help us? Exactly. Right. What we want to do is look at these, go back to these two critical values. Let's find out what the sign of the second derivative is at q equals 1. At q equals 1, the sign of the second derivative is minus 2 times 1. Here's our second derivative right here. Plus 12. So that's plus 10. So what does that mean, Ben, that the fact that the second derivative is plus 10 at q equals 1? It means profit is a minimum at q equals 1. Okay. Because this is positive. Okay. Let me just summarize this information again over here. We know that pi prime at 1 is equal to 0. Pi double prime of 1 is equal to 10, which is greater than 0. These two combined guarantee that pi of 1 is a relative minimum. At q equals 1, profit is a relative minimum. Also notice that pi prime of 11 is 0. Oh, I should have written 11 here. Pi prime of 11 is 0. And let's find the second derivative. What is pi double prime of 11 going to be? Well, if we just plug in q equals 11, it'd be minus 2 times 11 plus 12. This is minus 22 plus 12. This is minus 10. Okay. So we have pi double prime of 11 is minus 10. These two combined guarantee that profit at q equals 11 is a relative maximum. So if we now look at the sketch of marginal revenue and marginal cost, let's show that. Let's graph marginal revenue and marginal cost. Recall that our revenue function is 100Q minus Q squared. Marginal revenue, just 100 minus 2Q. So our marginal revenue curve looks like this. Starts at 100, has a slope of minus 2. So our marginal revenue curve looks like this. Would cross here at 50, wouldn't it? Okay. Our total cost function, recall, our cost function was this. So marginal cost, C prime of Q, is just Q squared minus 14Q plus 111. Okay. If we graph this marginal cost curve, it actually, let me erase this here. $111 will actually be up here. Our marginal cost curve is going to be U-shaped, it's quadratic, and it's going to look like this. It's going to come down, it's going to intersect marginal revenue here, it's going to come down, reach a minimum, come back up, and intersect once again. Okay. And I know what these intersections are. They're the critical values of Q. Here, you drop a perpendicular here, that's Q equals 1. Our first critical value. You drop a perpendicular here, that's Q equals 11. Okay. The marginal revenue curve intersects the marginal cost curve twice. And this one is actually a profit minimum. At this intersection, at Q equals 11, you have a profit maximum. Okay, so that's where you want to produce. Okay, all right. Okay. What price should the monopolist charge? Well, if you want to find the price the monopolist should charge for his or her product, how would you find that? Andrew? Okay. Yeah, there's one of two ways you could do it. You have this demand curve, Q equals 100 minus P. And we know the profit maximizing quantity is what, Andrew? 11. So you ask yourself, if Q equals 11, what is the value of P going to be? And the value of P is going to be 89. Or alternatively, you could use the inverse demand curve. Notice the inverse demand curve is P equals 100 minus Q. If you know that the profit maximizing quantity is 11, then you can directly find it. 100 minus 11, 89. Okay, so that is the price the monopolist should charge. Okay. Since marginal revenue intersects marginal cost twice in this problem, we really did need the second order conditions to figure out the maximum from the minimum. Okay. Or alternatively, you could rely on this kind of intuitive result. The firm wants to operate where marginal cost crosses marginal revenue from below. And that would be Q equals 11. Obviously, this doesn't make any sense, because if you were producing Q equals 1, why is it obviously this not going to be the maximum at Q equals 1? Did you want to answer, Jonathan? Oh, go ahead.
Couldn't you just graph the profit function instead of all three of these and gotten the same thing?
You could have. That's a good suggestion. Let's do that. But before I do that, From the marginal revenue and marginal cost, why is it obvious Q equals 1 is not profit maximizing? Just using your marginal intuition. Yeah, Johnny? Well, okay. If you produce a little bit more than Q equals 1, what is true about marginal revenue and marginal cost? Yeah. Your marginal revenue exceeds your marginal cost. So if you produce a little bit more and your marginal revenue exceeds marginal cost, then your profit's going to rise. So I would look at it that way rather than what's happening, say, to your average cost function. It's just that marginal revenue exceeds marginal cost for output greater than 1, so you ought to produce more. Okay. But, Jonathan, I like your suggestion. We obviously should look at this profit function and look at its graph. That's a good suggestion. I've erased the profit function, but we can quickly get it back. Profit is our revenue, 100Q minus Q squared minus costs, and costs are this. Minus 7Q squared here. Okay, there's our profit function. Let's simplify it a little bit by combining terms again. And we get minus 1/3 Q cubed. We get plus 7 minus 1 would be a 6Q squared. And then we get minus 11Q minus 50. Okay, that's as simple as we can get it. It is a cubic function. Okay, these cubic functions will generally exhibit one minimum and one maximum. Generally, not always, but their general shape will be one max and one min. So if we wanted to sketch this, it would look like this. What is the vertical intercept of this cubic function? Jonathan, if I could. What's the vertical intercept? In other words, when Q is 0, what is profit? Not 50, but negative 50. And it makes sense that it would be negative because you have this fixed cost of 50. So if you don't produce any output, you'll still have that cost of 50. So your profit would actually be negative 50. Okay. We know from our math that we have this. Recall, pi prime of 1 is 0. Pi double prime of 1 is negative. Oh, I'm sorry, positive. So at Q equals 1, we have a what? A local min. So what this means is this profit function is going to look like this. Initially, it's going down. It reaches a minimum at Q equals 1, then comes back up. Then it reaches a maximum at what quantity? 11. So you have a relative max right here, and you have a relative minimum right here at Q equals 1. What's that? All right. Yes, that's good. If we, do we have our second derivative function here? Yes, it's right here. If you really wanted the inflection point for this problem, you would set the value of the second derivative equal to 0. Now the value of the second derivative is minus 2q plus 12. Set this equal to 0, and as you said, Jonathan, you get, we'll call this q2 value is equal to 6. Okay. So what this would be, this point right here in the middle, almost the middle here. Well, actually it is the middle between 1 and 11. Is the point on the function where the function changes from being convex to concave. Okay. All along this section right here, the value of the second derivative is positive. It's 0 right here, and then thereafter it's negative. So this section right here is where it's convex, where the second derivative is positive, and this section right here, beyond q equals 6, it's concave. Okay, very good. I didn't actually calculate what the minimum profit and the maximum profit are, but if you just go back to that objective function, you plug in q equals 11 into this objective function, you get the maximum profit. And it would be this height right here. This would be pi of 11. Okay. Obviously, the minimum profit is pi of 1. And this would be something less than minus 50. Okay. And that would be the minimum profit. Okay. Interesting problem. Okay. There's a lot of aspects of this problem I like. I like, being able to graph this function. Knowing the first and second derivatives help you graph what the function looks like. So that's what our objective function looks like. Graphing marginal revenue, marginal cost is interesting too. Would make a good exam problem. Any questions over this? Yes, Helen?
So does that mean if you have a problem like that, you
Yeah.
can always, if you use you can equate the marginal cost by primary revenue or you can calculate the same primary.
Yeah, you could, but the problem with just doing the marginal revenue equals marginal cost approach is you get two values of Q. Q equals, in this case, Q equals 1, Q equals 11. Then how are you going to figure out which one of them gives you the maximum profit? That's the problem with the marginal approach taken by itself, is it doesn't give you necessarily the maximum, which is what you're looking for. Okay. The ideal way to do it is both ways. Again, ideally it would be best probably to start off with the objective function, the profit function, and use the classical optimization tools where you look at the first order conditions, the second order conditions, and then that'll tell you where the max and minimum are. And then I might later ask you, okay, graph marginal revenue, marginal cost. And the marginal revenue, marginal cost will intersect at the critical values of the Q's that you found earlier.